I'm happy to be here. Is this on or is it? Okay, great. And so today I'm going to be telling everyone about the joy of Axion theory. And in particular, I'm going to put QCD Axion, since these days it's not actually very obvious what you mean when you say the word Axion. So I'm going to talk basically about the original incarnation. The idea behind the QCD Axion basically starts off from the following question, which happens all the time, which is you have a composite object, which in this case happens to be the neutron. So you have your neutron, which is just some bag of quarks. And the question is, you have a composite object, and what is its dipole moment? So in particular, the electric dipole equals, dipole is what is it? And so, like any great theory, you sort of say, I don't feel like doing any equations, let's draw some pictures first and try to understand the problem and how to solve it before actually doing pen to paper. So the idea of a composite object with or without electric dipoles is very common. You probably learned it in high school about chemistry. And so there are plenty of molecules, composite objects. So to name a few, there is methane. Let's see if I remember. So methane is a tetrahedron. There is water, which has its own sp3 orbitals. And then there's carbon dioxide. So these are just a few of the most common ones you see in nature. And you can ask, what is the dipole moment of all of these guys? So carbon dioxide has a slightly minus charge on the oxygens and plus charge on the carbon. However, you'll notice I drew it in a straight line because that's how you observe it. And so its dipole moment of carbon dioxide is 0. Okay, let's go to, let's do methane first. Methane has tetrahedral symmetry. And so by symmetry, it's also 0. Oxygen, on the other hand, is an approximate tetrahedron where you have the pairs of electrons here and then the bonds over there. However, it's not an exact tetrahedron because obviously you can see sort of there's some asymmetry. This has some plus charges over here, making these angles not exactly, like 109.5. And so this has a non-zero dipole moment. H2O not equal to 0. So we can see from nature that there are a plethora of composite objects and a plethora of different dipole moments, right? And, well, since we are talking about the joy of things, one fun fact about molecules is that actually the fact that a lot of dipole moments vanish due to things like discrete symmetries, in this case tetrahedral, was.
But in case of water, you would guess that it could be a p-reflection of this plate.
Yeah, so reflection, so there's a few things to say. One, there are a lot of reflection symmetries you can write down, but there turns out to be a kind of a critical difference between water and neutron, which is that there's one neutron, and there is an infinite number of H2Os, all rotated with different degrees.
What kind of symmetry we're discussing? Because if it's not time reversal, if it's, say, p-reversal, reversal, then I would looking for mirror reflection of this.
Yeah.
Dipole moment would be.
So what happens with water under P reflection is it gets taken to a different water molecule, which is a rotated water molecule.
Right, but then when there is a kind of degeneracy, when there is a degeneracy, it means that the symmetry is still there, right?
Yeah, that's right.
That's why I asked.
Yeah, yep. And what was I doing? Oh yeah, I was talking about, I did a brief excursion into discrete symmetries, namely, we shouldn't look down on other fields. Chemists worked out the dipole moments of discrete symmetries, and in fact, also the quadrupole and octupole moments before mathematicians or physicists did. And so the fact that, for example, discrete symmetries forbid everything quadrupole and below, so you'll calculate the quadrupole moment of that is 0, 2. The octupole, you cannot prevent the octupole and above. These are just random facts that come from chemistry, not mathematicians or physicists. So I at least find joy in random facts like that. Helps keep us humble. All right, so great. So this is classical mechanics. And so what we want to do is basically say, okay, we've drawn some pictures. We've seen some ways in which, I'll talk about it a little bit more about how the problem can be solved. Well, this one you'd say doesn't have a problem. These two guys have zeros, and they have corresponding solutions. And so we want to then say, okay, we have some idea, some analogy to make. Let's sit down, bite the bullet, and do a calculation. And so what we're going to do is basically just go to QCD and calculate the neutron dipole moment, or just sketch how these things are done. I also personally find some joy in this because I think EFTs are wonderful. And so if you've seen this before, hopefully you'll enjoy seeing it a second time. Yeah.
Under certain conditions, you show that the electric path on one is exactly 0. And then you have to decide why, for instance, water does not satisfy the conditions.
Yeah.
But in this way, by itself, the space configuration then tells you that the symmetry is there if there is a partner of this, right? P partner of this. Right. So it is but for Newton, the symmetry does predict that if you believe that the symmetry is there, you do not need to calculate.
Yeah. Yeah. So there is a slight difference between H2O and neutron, basically due to how they behave under reflection. Namely, one configuration of water is taken to another configuration, whereas neutron is taken to itself because we only have the 2 spins of the neutron and no other degrees of freedom.
No, but with Newton, we know that there is no
Newton. Yep.
At least we can discover.
Yes, so far. All right, so let's sort of do a brief reminder of chiral perturbation theory and how much fun you can do with EFTs and spurions. So the starting point is just 2-flavor QCD, right? You have L is your kinetic terms, L kinetic. You have your mass terms. Let's write while fermions, like civilized people. So there's the mass term. There is, we're writing every term allowed by symmetries. So we have a mass term. We have a theta term. And so the matter content of our theory is QCD. We have our quarks, which I'm just going to write as doublets here. And so you have a flavor symmetry, SU2 left, that acts on the left guys. You have SU2 right, that works on the right guys. Let's see what else. You have baryon number, 1, -1, and you have U1A, 1, 1. And in addition to all of these, you have spurious symmetries, which this is one of. And I guess actually everything here except for U1 baryon is. In particular, you have spurions, you have a mass term, fundamental, anti-fundamental. Mass term, which has to transform as anti-fundamentals under SU2 left and SU2 right. It looks like it has 0 baryon charge, it has -2 U1A charge. And the last one is how does U1A transform? I've already written how the quarks transform, namely e to the I alpha. Q goes to e to the I alpha Q. Q conjugate also goes e to the I alpha Q conjugate. And as you all know, when you do a this field redefinition in the path integral, it's anomalous. And so to make this a symmetry, you also have to send theta to theta minus 4 alpha. So you have a few symmetries, and in fact, you can write down anomalous symmetries that don't respect the SU2 left and SU2 right. But this is just an example of one. And so at this point, you need a little bit of help from experiment, namely that you learn the symmetry breaking structure. So you basically learn that SU2, the two SU2s are broken down to the diagonal. SU2 diagonal when, I guess I'm going to call it U, when this matrix becomes non-zero. And in particular, let's write it as e to the I whatever, I'm not going to be careful about eta versus eta prime here. Identity matrix, e to the I pi a ta over f pi times some number that's roughly 4 pi f pi cubed with some order 1. Okay, so experimental fact, the symmetry is spontaneously broken. We're going to be getting Goldstone bosons. And so what we do is we just write every single thing possible that respects both your real symmetries and your spurious symmetries here. And so when you write down everything allowed by symmetries, what do you get? You get kinetic terms like mu, trace. It's probably, I guess if I choose TA to be trace a half, then that'll be fine. We can write, yes, one of these is U dagger. Okay, so then we can start doing perturbation theory in M, write terms leading order in M, next to leading order in M. Let's see, that's going to be something like some constant. I'm just going to call it A, f pi cubed, trace of mu plus hc. And then you can have higher order terms. Let's say f pi squared, some other constant. So you could have this trace m squared. You could, I think there are maybe 3 or 4 of these guys you can write down. Dot, dot, dot. We're going to work in the limit where the masses are all very small so that we can neglect those. So that's basically the first spurion M. Next spurion we have to take care of is theta. So there is, well, it's a little annoying. Oh well, I don't have space, not good board management. All right, so first there's theta QCD. I guess I should be, where we can say, okay, we know how the quarks transform. We know how theta transforms. We know how U looks like in terms of the quarks. And so this just tells us, since it looks like it's a pure rotation, how your eta prime guy transforms. And so you can just write a mass term. This is what there's going to be theta. And okay, I guess if I work through, you're going to see that the eta transforms by 4 alpha. 4 or 2? It depends. Oh, I guess it depends how I normalize things. Oh well. Theta prime over 2 squared is actually a slightly more complicated function because you'll notice this is not a periodic function. Since everyone was telling me what to talk about, and I'm up here, now I get to say, go talk to Csaba if you want details about this. But, okay, so this is theta QCD. And since we're actually ending up, I forgot to write it down, gonna end up talking about electromagnetism, we can also do the exact same arguments here to write down couplings to FF tilde using the fact that we can do Carroll transformations again and just do the exact same thing here by just writing everything consistent with symmetries. So FF tilde e squared over 16 pi squared theta, and then we're going to write things consistent with symmetries. So what you can do is things like u goes to u and uc, both go to e to the I alpha u and or uc, which, let's see, sends theta to theta minus its charge squared. I did it with two particles, 2 alpha. Might as well do this with the down quark at the same time to make it goes to e to the minus I alpha down quark or the down quark, which also sends, let's see, opposite sign because I put a minus sign, so it's plus 1/3 times 2 alpha. And I chose this transformation very carefully because when you write it in terms of this matrix here, which you can just write it as UUC, UDC, DDC, UCD, you'll notice the only thing that transforms, this does not transform, this does not transform. The only thing that transforms is the diagonal. So I'm basically specifying how the pi 0 transforms. So this is the pi 0, or rather e to the I pi 0. So this is pi 0 over f pi. I think I was choosing TA to be a half sigma z, so there's going to be a 2. If I want to just specify the top guy, it goes to pi 0 over 2 f pi plus 2 alpha. And the down part is also this. Okay. So modulo math errors, I have told you how the pion transforms and how the theta E and M transforms. You can be explicit. And so we can say this is in fact even a nice number, 2/3, 1/3. This is minus alpha. So that looks like if this goes to minus alpha, this goes to a plus, so that's a plus sign. Plus 2 alpha. Okay, this looks like, if I have it right, let's just write it as the way people like to write it. Trace of q squared, which is this. Let's see, the minus plus. Okay, I think that's right. Pi 0 over 2 f pi here. Okay.
So does
Yeah.
the fact that our more formal friends would now say that the ABJ anomaly with electromagnetism renders the axial symmetry non-invertible, does that usefully inform the Spurian analysis? Does it organize information in a more compact way?
Not as far as I know. In some sense, yeah, the fact, yeah, I don't really know exactly how that interplays with this Spurion, which is in some sense a much more bottom-up type way of thinking. But
Electromagnetic actually is not effective. It was kind of Anson, Anson was discussing this long ago. I mean, you can discuss another paper, right?
well, I think.
It doesn't fit money. Doesn't show up.
Oh, yeah, flat space, true.
Yeah.
Flat space theta, electromagnetism.
About this effective variation, I believe what has happened is there is a term which corresponds to eta prime goes to 3 pi.
Yeah.
And it follows also from
Yeah, so
I mean, it's
I'm only getting part of the whole what Wooden got, right? Like I'm just getting the simplest piece.
Terms which are kinetic contains that, but I mean, I remember because this was the first what we showed that the term containing theta together with eta prime goes to 3 pi is follows from the C.
Mm-hmm.
You see, so I think it's relevant to what you were discussing.
Yeah. I guess if I wanted to start calculating decays and things like that, yes. And
Because it's this way,
but
it's only limited number, but there are more terms which are still kind of reflect this Carl's-Unity, and which refers to interplanetary decay. Because here there is no interplanetary decay.
yeah. No. Yeah, I'd have to look back at the people who did the non-invertible symmetries to double check just to see. It's not obvious to me if they're, when they define their operator, if it actually transforms under the spurious symmetry. Because if it did, then you might be able to start saying stuff and tie the two together. And
pi 0 is a consequence of anomaly matching for the non-invertible symmetry. The question is, like, is there any content to that beyond what we would already said without invoking the non-invertible?
Yeah, because I guess they would have said this is the result of anomaly matching. I would say this is the result of spurions. And I think people even older would go to current analyses about getting the exact same thing.
The next question is, is there any daylight between these explanations? Or is there any added explanatory power?
I think you can, yeah. I think the older current way of looking at it, the spurion way, you can connect a bit. I'm not sure about the non-invertible stuff. Yeah.
Oh no, it is now. The technology has come further. In the original Schuhan paper, it was only irrational. But now they can do it for
I'm glad you see, because I remember it very well, because historically our paper was the first to show that the physical relevant amplitude associated with theta. And we played this game of Carl-Unity, for interplanetary decay. Because some people at that time doubted that theta is effective. I mean, okay, so the written paper was later about data mode, it was later on, but the interplanetary goes to 3.5 was the first example that related stuff at that time.
Yeah.
So sorry about this memories.
Yeah, you can see a lot of the, in fact, the way we'll do it in a moment is you can integrate out the eta prime to get theta, QCD, into other terms, like the Meson's terms, and then you can start getting all these CP breaking effects from, yeah. Okay, so I guess let's just do that. It's pretty clear how to integrate out the eta prime. You set it to its vev, which basically just puts theta out here up to a factor of 2. And then we're just going to, first step, find how does the vacuum energy depend on theta. So in other words, we're going to integrate out eta prime, and then we're going to integrate out the pi 0. E and M isn't broken, so you don't need to deal with pi plus pi minus. So if we take this term, what is it equal to? You have A, f pi squared, trace, mu, e. So I'm going to write masses and separate out their phases just to make explicit other effects. E to the I theta d. We're going to get, let's see, this sets it equal to theta over 2. So and I seem to remember it should be theta here, not theta over 2, but I seem to be getting theta QCD over 2. And we're going to get the pi 0. And let's just not write a lot by saying the vev of your pion, pi 0, is phi. So that looks like I'm setting pi 0 over 2f pi is equal to phi. Okay, and now this turns out to be easy. We can multiply exponentials pretty easily. We can even add their Hermitian conjugate. This turns into a cosine. This turns into a cosine. And then just minimize. Take this guy derivative with respect to the pion, so phi, and set it equal to 0. And we're gonna, let's not, you're gonna get tangent phi equals mu minus md, mu plus md, tangent theta bar over 2, where theta bar is just the sum of the thetas. Oops, theta QCD plus theta U plus theta D, which is basically what you expect because of other anomalous symmetries, which I didn't write down, which, well, I guess I had said already that the mass matrix transforms under anomalous transformations. So it's not surprising that you can remove, shift around the phases, theta. And this turns out to be the only thing that's invariant under all of those sort of anomalous shifts you can make up. Okay, take this, plug it into your potential, and you get that the potential, the function of theta, I guess I will comment in a second about mu plus md squared sine squared theta bar over 2. And so you get a final answer. I skipped a step, which is how to relate this stuff to the mass of the pions, but you just Taylor series this, and you'll relate this coupling to the mass of the pion, which you can measure. And so you have a very concrete prediction plus higher order terms that are higher order in your mass, m squared, m cubed, etc. Okay, so clearly you have some theta dependence of your vacuum. Since I have both equations written here, you can even see some other effects that sort of have confused people before, which is if you take this expression, which is your pion vev, you plug it into your theta, or your coupling here, what you will get is that the coupling here is like e squared ff tilde over 16 pi squared theta e and m. Okay, that's roughly 1. And I think, is there a 2? Okay. Either way, arctan, there might be a factor of 2 here. mu minus md, mu plus md, tangent of theta bar over 2. So just sort of going back to other talks in this week, when you heard Chaba's talk, he was also talking about these sort of effects which are not entirely periodic as you change theta bar and things like this. And so I'll comment again about this when we talk about the Axion, but for now, oh, I guess I also didn't write the eta prime piece. Okay, plus an eta prime piece, which I'm not writing right now. Okay. Great, so just very briefly, oh, going so slow. Let's talk about just how we connect this to the neutron EDM, because that's how the original experiment was. It's not the strongest constraint these days, but for at least some period of time, the neutron EDM was the strongest constraint. So the way we do this is we have to add neutrons to chiral perturbation theory. So you define a neutron field which contains the neutron and the proton. And then again, write all things consistent with symmetries. You're going to get things like a mass term, m. Okay, this I might n and c. You have a mass term with some coefficient. And these things all have names because they've been measured. You have just a straight up mass term, minus mn. N, is this a U or UC? U dagger, and C. And then there's one last one that actually is important. You're just writing all terms allowed by your SU2 left and times SU2 right symmetry here. Where was this in my notes? N, U dagger, M, U dagger, and conjugate. Okay. It's messy. You shouldn't be able to see it, but you Taylor expand these guys to get pion couplings. And then you draw the following diagram. So a photon, charged pions, neutron, proton, neutron. And you can get the expression Ben wrote on Wednesday, which is the dipole moment. This generates the dipole moment for the neutron. The dipole moment of the neutron is 3 theta bar E times centimeters. And hopefully I guessed it right. Okay, great. And so you get an answer, which is just the dipole moment should be of order, which you can even say this is roughly speaking charge of the neutron, Q neutron, charge of the constituents, Q of the quarks times the size times theta bar, roughly.
I think that it's important to emphasize that
Let's write size.
pion vertex is the one which brings preparity.
Yeah.
The part which is proportional theta.
Yeah, one of these. Yeah.
Not in gamma interaction, but in the vertex.
Yeah. One of these. This one is proportional to theta bar.
Right, I think, and
yeah.
In this sense, it's again chiral Lagrange.
Yep. Yeah. And in fact, you'll see this coupling is not just proportional to theta, it's also proportional to the mass mu, for example. There's quite a few things you can say about it. But for now, measure these things, go to your experimental colleagues or your lattice colleagues and measure, ask them if they can tell you these coefficients. They come back, they tell you what they are, and it turns out the answer is exactly what you expect, which is charge of the quarks times the size of the neutron, roughly, times theta bar. Well,
is that the case with like previous, is there a lattice calculation starting from GCD?
Let's see. So probably, I don't know of any exactly. Some of these you could definitely measure on the lattice. So some of these are like the difference between the neutron-proton mass and things like that. Well, at least, for example, the quark contribution to that, which you can get on the lattice. Other things you mostly get from scattering experiments. So I'm not sure about so you can get one combination of these three couplings. I'm not sure about the others.
Just in the sense of like, every time a paper claiming this strong CP problem is not a real problem is in the archive, and you sort of have a conversation with colleagues, and you can't say that there is just a first principles lattice calculation with non-zero theta going from the Lagrangian to the neutron EM. You always wish that existed.
Yeah. This diagram, which is here, is they play this logarithmic enhancement. That you have this loop, and the loop, because of mass of pion is less than nuclear mass, so it's a kind of limited accuracy, right? But I think that the main element is still this vertex, parity violating vertex of pion, right? Probably lattice still could.
I see a lattice. I guess.
You're referring to these papers by Shearholtz and others.
Yeah.
I really would take the claims with many grains of salt. I mean, they are just the numerical evidence is, they're not at the physical point. I mean, so there's, I would not. I mean, I think it is kind of a, it's meant to be controversial, I think.
You mean just calculating this pion vertex itself?
No, I'm talking about the papers that have come out by people like Shearholtz that are claiming that there is evidence from lattice QCD that there is no strong CP problem.
I see.
And so I would. Okay. There are no calculations that include the theta term directly, the Lagrangian. There is quite a bit of work being done to, you can compute the operators, of course, and there are all kinds of computations they are like the Los Alamos group is working on computing all contributions to the GMPDM. This is still an ongoing project.
But in this sense, if you will see,
Lance had something. We should try to get
the continuum limit data area does exist, right? Then it's some problem for lattice theory itself, right? Because there is no consistency between continuum limit and lattice calculation.
I'm not sure I understood.
Amplitude proportional to theta are proven to exist in MQCD, in continuous limit. And there is no loophole in this field. Okay. Now we are saying that lattice saying that there is no this, then I view it as a conflict.
So I'm saying that you should take those claims with a grain of salt, many grains of salt.
Right, lattice might, oh sorry, Lance?
I wouldn't say that, I mean, I don't think that, there are claims, but it's not established.
Yeah. Okay.
Yeah. Right.
It's a very hard calculation, it's very noisy, so
Yeah.
people are trying, different groups have been attempting this, but they don't have good enough statistics yet to be able to resolve this.
Lance?
Just there was going to be a conference in March, and there's going to be a talk on putting data on the lattice, so maybe stick around for that.
Yeah, it's hard because of the sign problem, and I mean, people have calculated derivatives of this guy, but not, yeah, the neutron EDM directly is difficult.
But also there's another way you can do a model calculation, which is the Scrum model, which is at large N, and it also gets a number that's comparable to this number. It's a little different though, because normally it doesn't have a logarithmic divergence as the ion mass goes to zero. So there's some weird lack of commutation between the large N C limit and the N pi goes to zero limit for this quantity.
Huh, okay. Interesting. All right. So I was only going to make one more comment about the standard model before finally getting to the Axion and sort of solutions to the strong CP, which is, this is a fact basically unique to the standard model, very quick. If you try to poke the standard model at all, you very quickly break this statement, which is the beta function for theta, or a theta bar, let's say, turns out to be extremely small. This is 7 loops. And this means that people haven't calculated it. And in fact, I don't know if they've even drawn the diagram accurately for this. But what they do is a spurion analysis. So you have SU3, Q, S, so the flavor symmetries of the standard model. You see, you have your Yukawa couplings, and you just ask the following. All of the CP violation in the standard model exists inside of these guys, your up and down Yukawas. Write something complex here. Just try it, and turns out to be ridiculously hard. Like the most simplest thing you can write is something like, oh, y dagger, it's a singlet, so you trace it. But you'll notice you're multiplying it by its complex conjugate. The CKM matrix does not appear here. And so just by dint of trying to write everything possible, what you get is that the best you can write is g squared trace. Okay, I'm just going to be very schematic. I'll leave it as an exercise for you guys if you feel like working out the details. Some of these are daggered. I can't remember which ones. But basically, you need to write 4, 8, 10, 12 Yukawa couplings before you can get something that is non-zero. In other words, not equal to its Hermitian conjugate.
And this is not related to the
Yeah, that's right. Well, I mean, this is proportional to the Yaroslav, but right, because in some sense the Yaroslav has to make its way into here, and it just turns out the flavor, because CP violation is so tied up with flavor symmetry, you can't write anything down. As soon as you do anything like whatever people's favorite things like supersymmetry, you get one loop running again. And from SUSY, it's the mass of the gluinos, or phase of the mass of the gluino, starts inducing one loop, because CP violation is no longer tied with the symmetry. But this really annoying fact, I say it's annoying because it opens the gates, meaning that if you set theta bar to 0, be it by hook or by crook, somehow it stays 0, basically. Which opens a pathway to a lot of solutions and a lot of people complaining. So. That's why I started writing theta and then switched over to theta bar, because they're really more the running of the phases of the masses of the quarks. So if you want to, yeah. So theta doesn't appear in perturbation theory, but theta u and theta d do. And so those can run, which then means theta bar runs, even if beta function of theta is 0. Right? And so you could say the beta function of theta is 0, but the beta functions of theta u plus theta d, which is what this is non-zero. And so technically speaking, that's what they write down. Okay. Great. So, yeah. Yep, it's there just as a spurion, basically to let me write the pion coupling. And in some sense, it's great that it does nothing, because I know exactly how it appears in the UV and exactly how it appears in the IR. Because E and M does not become strongly coupled. I don't have any instantons to worry about or anything. Great. Yeah. All right. Okay. So, great. So we finally set up the problem, and let's look for inspiration for solutions from the classical examples. So the classical example which had 0 dipole moments are methane and carbon dioxide. Okay. So both of these have different aspects to their solution of why the dipole moment is 0. This guy, you can just say, the moral I'm just going to say to take away from methane is that discrete symmetries work. So discrete symmetries. The second is carbon dioxide. And what happens here is, it actually happens for them both, it's just easier to visualize for carbon dioxide, is that I could give carbon dioxide a non-zero dipole moment. I have experimentalists friends who are very good at what they do, and they can bend carbon dioxide for you. And you'll notice this has plus, this is minus, minus, and so as a dipole, well, probably normally defined the other direction, but whatever. And that's not 0. And so you could ask, well, what gives? Why do I see a bunch of these guys and very few of these guys? Only when people work hard do I see a bent carbon dioxide. And the answer is, well, sure, you can bend carbon dioxide, but as soon as you let go, this guy starts to oscillate back and forth. It'll do things like emit, it's a charged particle, dipole moment oscillates, it emits light, it emits photons, and turns into a flat guy.
No, it could be different conjecture. That you have, say, curved CO2, but there is a kind of a mirror reflection of the CO2. It would be enough. You do not need...
You don't need it, but this is what happens.
No, because there is
in the end,
stable stuff. But
yeah.
I mean, imagine that it would be stable
Yeah.
with the angle,
So,
it would be reflectional.
Yeah, that's right. And so it turns out,
even in some sense, this methane, which you can bend and get it away from the tetrahedral symmetry, this is the solution to every single, at least I've thought about this for molecules. In molecular physics, this is the solution for every single small dipole moment, is it can relax to 0. So given that every single example in chemistry, this happens, what do we expect in QCD?
What about sugar? Sugar. Sugar is
Not familiar with this.
left-handed sugar and right-handed sugar. They are different.
Yes, they're different, and
in the nature we have more.
And they have non-zero dipole moments.
Right.
Yeah, so that's why I said the ones with 0 dipole moments.
No, but I mean that you said that nothing in chemistry. I'm trying to find something in the chemistry that would be, example.
Yeah, so I'm just saying, in chemistry, every example of a composite object that has 0 dipole moment has 0 dipole moment because it relaxes to 0. So
but those which are non-zero,
they relax to a non-zero number. Yeah. And so given this is the case, and given that we have observed that this is more like the neutron, this sort of behavior of 0 dipole moment, basically I would say Murphy's law is that it's the exact same boring solution, right? We've seen it before. It solved every other example. Might as well be the same case here. I would say it's, so when I said this to my wife, she says, I disagree with your definition of pessimism, but my thing is, well, it's sort of like back when you're in love, where it's the only thing worse than being hated by the person you love is not even being acknowledged you exist. And if we're so special that we find something that just looks like it was designed just to twist the knife into us, at least we have the acknowledgement that whatever got up there is treating us in a special way. I find that slightly more optimistic than saying they just don't care at all, and all good things and bad things come from negligence.
You are ready to sell
But,
the marriage console.
Yes. Okay, so what is then the analogy here of how do we make, or how is theta relax, how do you relax it? So the weird thing about QCD is that this angle doesn't automatically exist, this degree of freedom, right? In carbon dioxide, this automatically exists. And so in the Axion solution, whoops, that's not an A. Axion solution is that this angle is dynamical. Theta, dynamical. So there are two ways to do this. The first is the massless up quark solution. So if the up quark were massless, it turns out the eta prime is exactly this angle that dynamically relaxes theta. Its VEV, basically, we found it in chiral perturbation theory, right? Its VEV is proportional to theta, and it ends up removing it entirely from your Lagrangian. So given that this is in some sense the thing you would actually absolutely expect, this automatically came for the story in carbon dioxide. Does it automatically come to the story for us? We go to our lattice friends, right? There's a long history of theorists trying to come up for reasons this is true or not true. There is a Cohen-Kaplan sort of ambiguity that makes it hard for theorists. So you just go to people who can actually do the calculation and ask them what is the answer. And the answer is the up quark mass is non-zero. Yeah?
So the up quark runs with a beta function before 7 loops, right?
Yes.
So how are those two facts consistent?
So I would say the massless up quark solution, it depends a little bit on how you exactly phrase it, but it's just at some scale, the up quark is massless, or put another way, you start generating the up quark mass through loops, through instantons, etc. and its phase turns out to be exactly opposite the phase of everyone else. And then you add up theta plus theta, theta bar is still 0. Or at some RG scale, there's essentially a U1A.
Are you saying that any RG trajectory which passes through a value of mu equals 0 at some scale, there will always be some RG invariant notion in which theta bar is 0?
I think that's true. I mean, if theta mu equals 0, it stays 0 at perturbation theory, and so you need instantons, and then all hell breaks loose. But instantons, you know their phase pretty well, because it's always, aside from the instanton action, e to the minus 8 pi squared over g squared, you get plus I theta. And then you get zero modes, which do things like put MD, MS, masses of quarks, which then also have their own phases. And so it turns out the phase you generate for the up quark mass is exactly negative everyone else. But, yeah, Lance.
I thought the massless up quark solution was not that theta was dynamical, but that it was unphysical.
Yes, and it's...
In other words, if it's dynamical, I expect some...
Yeah, so what you can do is take the eta prime, work really hard, push it away from its expectation value of 0, and its processes in the chiral Lagrangian mimic that of a theta bar being non-zero.
But I think that if at some point mu would be 0, then theta dependence would disappear, and then I mean you would say, aha, it's always 0, like you argued before. So yeah. I think that the main point actually in appearance of theta dependent is U1 problem. That this instanton solution, it's example where no, I mean not example. It was a resolution of U1 problem, conceptual. That U1 symmetry is not there.
Yeah.
And theta dependence that does appear only because U1 problem is solved. Because U1 is broken. If U1 is not broken, there will be no theta dependence. Right? Yeah. So in this way, showing this instanton, in this respect too, right? That it shows that U1 problem could be has a resolution, right? That the U1 is broken indeed, and then together with this theta dependency.
Yeah. But I think the concrete statement is at the level of chiral perturbation theory with if mu equals 0, the eta prime vev acts like a theta angle. Yeah. But of course, any value other than 0 is just an unstable configuration. So maybe you push it off, hold it there, and then look at pion decays and things like that, and you would see all the CP violating stuff. And it would act like theta was non-zero with eta prime, with the eta prime vev. Sort of like carbon dioxide. In order to get a dipole moment and do any physics that sees the CP violation, you have to bend it and you have to hold it there. And so I'm just saying, if you bend the eta prime or push it off and hold it there, then it acts like a theta angle. So in that sense, it's sort of very analogous to carbon dioxide.
But in normal QCD?
In normal QCD, the answer is no.
In some ways better.
Yeah.
No, because you do have theta dependence.
Yeah.
Yep. Non-zero mass of flow.
Yeah. And so this would be the best solution. It would be awesome. Most analogous to everything else we've seen. Turns out it's wrong. Okay.
Anson, sorry,
Yeah.
I have a follow-up to what I asked before. So I've seen people say that this solution doesn't work because of lattice determination of the upward mass at a specific renormalization scale in MS class.
Yeah.
But if it
and
back to if it runs, so is that sufficient to guarantee that the massless upward?
Yeah. So that value turns out to be larger, much larger than any instanton. Even if you start from the Planck scale and run down, like look at all instanton corrections in the region where you still have perturbative control, okay. That number is much larger than anything.
I see. So it's not as simple as comparing to 0.
Yeah. So if you found that it was very small and it happened to have a value roughly equal to the instanton value, then you might be like, maybe it's 0 at the Planck scale, and then everything we see now comes from instantons and whatnot generating a non-zero value.
Okay.
Yeah.
Do you know roughly what that value is, the instanton? It's like 0.5 or 0.005?
Back when I was younger and smarter, I did, but not now. I have forgotten everything. All right, anything else? Okay.
But
So,
in terms of proving that dependence with non-zero metaphor, technically we are not independent to instanton because chiral symmetry is enough to prove that, I mean, if you want problem is resolved, then writing, this chiral invariant stuff, or say, either prime interaction or say, pi nuclear deltas, is enough to prove it without reference to instanton, right?
Yeah, so for me, the most effective, convincing thing is just chiral perturbation theory. Okay, so given that the most elegant implementation of the Axion doesn't work, that's basically what this is called. I think people didn't realize what they were doing was analogous to carbon dioxide way back when, and so they renamed it. And so it's called the Axion solution, which is given if QCD is not nice enough to make this angle dynamical for us, we're going to just do it ourselves. So you start off, you just say, well, theta appears in your Lagrangian like 32 pi squared g squared. And so we're just going to add something whose sole purpose in life, A over FA, is to make the theta angle dynamical. So we're going to write this down and write nothing else, plus 0. One new guy. And so you can see all it ever does is its vev acts like theta. And okay, and so given that we now have this guy, you can ask, is QCD more like carbon dioxide, or is it more like water, right? We had said water was almost 0, but because of its orbital structure, it had a slight dipole moment. And so when which you'll also notice you can bend and play with oxygen and have it relax. So the question is, when this guy relaxes, does it relax to 0 like carbon dioxide, or does it relax to non-zero like H2O? And this is just a question you have to answer. So, but this is why I went through and calculated V of theta for us, because if the way you go from this new theory to any old theory is just replace theta with theta plus Axion over FA. So we have our Axion potential then, which we've calculated. dmu plus md squared sine squared theta bar plus A over FA over 2 square rooted. And at this point, those of us who are a little younger, we've forgotten how to do math, so we just plot this. And you find, if this is A over FA, let's see, I put it with a plus sign. So it has a minimum here. I guess it's even periodic. So, and at a value of A over FA equals, I put a plus, so that's a minus theta bar. Okay. So this means that given that everywhere you see theta, you replace theta plus A over FA. Once you plug in A over FA, this means every time you see theta, you plug in 0. In other words, this is really more like carbon dioxide. It relaxes you to the nice CP invariant, CP preserving minimum for the Axion, or for QCD. And so it really does implement exactly what I said here of making the angle dynamical. All right, so, and in some sense, it is also a very pretty picture in the sense that I only needed to add one particle and one interaction to get everything I wanted. Okay. I guess the one other relevant thing, since you can even get this equation that Ben was using, which is the Axion photon coupling. And so remember, I had said you replace everywhere you see theta, you replace A over F, which means in the FF tilde coupling over, okay, so for reasons I don't fully understand, the convention is to put FF tilde over 32 instead of 16. But you have the Baire coupling, A over FA, the Baire, whatever your UV dependent thing, could even be a plus sign, UV dependent. So in other words, in this case, I didn't write it down, so this term would be 0. This is, they often call this E. And then there is a piece that comes from the pion, which we had said was, I can't remember the factor of a half, mu plus md minus md, mu plus md, tan theta bar over 2, and now this was plus A over F. And then there's the plus the eta prime piece, which I had not written down, so I don't remember what it is. Okay. And so this just means you can Taylor series this and get the Axion coupling to photon, which is what everyone uses when they look for it. And so you see, this just gives, Ben defined the coupling GA gamma gamma, which is, let's see, it's alpha E and M over 2 pi minus 1.92. Okay, so just some number, which this is basically your Baire coupling. The, did I get, this is an FA, right? This is your Baire coupling normalized by how you define FA. And then this piece is just chiral perturbation theory. Comes from a mixture of the eta prime and the pi 0. Okay. Great. So this is the Axion. And so for, well, I only have 20 odd minutes before lunch, but let's sort of outline what is going to be the rest of the conversation. So let's see. The overview of the remaining. We'll see how much I can actually cover. First, we'll just sort of briefly discuss why do you even have this AGG tilde coupling? What is a UV completion that does this? Ben has already given one example, which is the one Arkady came up with. Because you've already seen that, I might just talk about a different one. Second, why no others? So this is saying, why do I not write anything else? And this should actually surprise you, or you should know that it's actually not true, that there is always other stuff there. Why? Because quantum field theory is kind of like a baby. Anything you tell it to do that's allowed, it will do. Anything that's forbidden, it will also do, until you actually put your foot down and say, this is impossible. It'll push you right up to the brink. And so that's what quantum field theory is like. It will do everything. And so you told it to act like the angle in carbon dioxide. It says, great, I'll do that, but then I'm going to go run off and do some other stuff at the same time. And so turns out there is always other stuff there, and you need to work hard to make sure there's nothing else. 3, what else did I say?
What you mean with others? You're looking at the lamppost, right? Because
Yeah.
you're looking for something which could cancel.
Yep.
It doesn't mean that considering some scalar particles, whatever, you cannot introduce CP break, you still can do it without all this stuff, right?
Yeah. And it's just, so in some sense you can say, like, to make this more motivated, what would you really want in something which you think looks aesthetically pleasing, let's say. Yeah. Next, I'll talk a bit about Axion strings and sort of basically fun stuff you can do with Axion strings and just sort of interesting properties. There's a lot of nice topological things you can say about it. Let's see, the other ones will be will be signal building, which is basically the statement that the QCD axion is hard to look for. If you want to convince an experimentalist to do anything, you're going to need benchmarks on the way so that you don't just tell them, make your experiment 10 orders of magnitude better. I'm going to ignore you now while you work for like 100 years to get those 10 orders of magnitude. So you want to do better than that. And so there's a bit of signal building to sort of see what does it take, and also not just signal building, but just a little bit of what are the signals that you can look for when looking for the QCD axion. There are a lot of fun things to look for, ways to look for it. 5, I'll briefly comment about gut axions. The basic motivation being the only thing better than a greatest hit is 2 greatest hits smashed together. And so that's how pop songs are made, and it seems to work very well. So let's do it in physics. And then finally, if I have time, I'll talk a little bit about axion dark matter. All right. Ooh, I have only 20 minutes. Jeez. Okay. So first, why the axion coupling? GG tilde. Okay, so we've already seen a first pass of this on Wednesday. So I'm just going to give you a different one, which again, the theme of this show so far has been that anything that happened in the past is the most likely thing to happen in the future. And so what are past examples of this type of coupling, and how do we, just say, well, that's the most likely thing to happen again. So, in fact, we've already written something that has this coupling and looks a lot like this. It's called the pion. It's the pi 0, FA, FF tilde, right? So the first thing you might expect is, well, the pion is basically an axion-like particle. Okay, it couples to photons instead of gluons. It has F pi instead of FA. But basically, it's the same thing, right? It happens to be quite a heavy, 100 MeV heavy thing, reasonably strongly coupled. But it's an example of what we've seen before. And so what you might very reasonably expect is that the axion is also just, well, it's a new pion of some sort. So in other words, this is just saying, well, okay, we've seen this coupling before. It came as a result of confinement. And so let's just say repeat, rinse and repeat, move on.
In the case of pion, you could refer to theta electromagnetic.
Yes.
Suppose that it doesn't work. So in this way, indeed works as an axion, right?
Yep.
So in this sense, it's a good example for you.
Yeah.
I mean, that it does work.
Mm-hmm. So what does it take to turn the axion into a pion? That's just going to be the first example. So this was, I'm just going to write the most obvious thing, which turned out to be what people did, the very first example, which is you had 2 quarks, QQC, that's charged under SU3 QCD, and there's some new SUN, whatever, call it SUN axion. And its sole purpose in life is to confine and generate a new pion that we're going to call the axion. So turns out just writing these 2 is not quite enough. So you write out 2 new guys, whatever, psi C, and away we go. So this guy confines, just like U confines. Here we get a QQC, Q psi C. This looks like a QC, so this would be a psi QC, where this is a 3 by 3 matrix. This is a 3 by 1, 1 by 3, etc. And this guy has a pion in it, which is 1, 1, 1, minus 3. This is a 4-dimensional thing, so this thing doesn't have a name, but we're just going to call it the T axion. And this guy turns out to be a massless particle that, so I very explicitly did not write a mass term for these guys, but is a massless particle with exactly this GG tilde coupling. So what you can do is what we did before, say Q goes to Q e to the I alpha, QC goes to e to the I alpha. Okay, so that will transform this guy. I need to make sure this guy, off diagonals don't transform. So this looks like psi and psi c goes to e to the minus I alpha, psi c. Great. And then this goes to minus 3 times. Okay, there's a factor of 3 I'm probably missing somewhere or another. But okay, but this basically is an anomalous transformation that sends theta QCD to theta QCD, whoops, minus probably n alpha, 2n alpha. And so you'll see this axion-like particle couples to QCD with a factor of n here. So all right, so this means you just get a n a over fa g squared over 32 pi squared gg tilde. And because the mass of the quarks are 0, you get ma equals 0. Right, just like the mass of the pions are normally some number times f pi times mu plus md. If you set the quark masses to 0, you can get a massless pion. We had said we needed only this coupling and nothing else. So we can set the quarks in that sector, their masses to 0, and you get an axion-like particle. So this is, I guess we had seen another way on Wednesday, but this is another way to get the axion. And you'll notice it's reasonably concise. There's one one free parameter, and that's about it. FA is basically the confinement scale of this SUN axion. Okay. So only 10, 15 minutes left. Okay. So I'm going to make a bit of a sidestep, go off on a slight tangent, basically because I guess Josh had mentioned the factor of 5 between dark matter and baryons, and then afterwards Ben said that the FAs less than 10 to the 11 GeV were not particularly well motivated as dark matter. And so I'm just going to give an amusing counterexample in the context of this model. And so what I'm going to do is add just a single particle with a single new coupling, phi over f. So this is just a brief excursion into dark matter dealing with this factor of 5. And it's going to couple to g, let's call this gn squared. So in other words, I'm adding, there are plenty of theory reasons why you might not be unhappy. You might be unhappy adding just this coupling and nothing else, but let's not get into it for now. If you add the coupling phi over f times gn squared, what does this thing do? It modulates the strong coupling scale of gn. And so this basically just means that lambda n, which is fa, is dependent on phi over f. So this is normally proportional to e to the minus 8 pi over g squared. And I guess there's a 1 over beta function, roughly speaking. And so g squared depends on phi. And so this is just saying this thing is proportional to e to the some number phi over f. Okay, turns out just by postulating this, we have basically solved the axiom, the y is rho dark matter equal to 5 times rho matter. And to see this, let's just say what happens. So we're going to have to write, our goal is to find the minimum v of phi. And I'm going to write just the finite density piece. So people are going to be unhappy not writing any vacuum piece, but bear with me. This is going to be m axion as a function of phi times the number of axions, plus m dark baryons, which is a function of phi, times n baryons. And I'm just going to minimize, find the origin, or find the 0. So we already said we know how FA depends on this new scalar. Let's just write how lambda QCD depends on this scalar. Basically, if you've never seen it before, the easy way to get beta function, confining scales and things like that. This is, if you've done, this is the, let's see, IR. This is beta UV times masses of particles to the 2 over 3 NF. So you see confining scales written a lot like this in SUSY. It's also true at one loop beta functions. And basically what happens is, oh, why did I erase it? Okay, the confining sector has QCD colored particles. And when it confines, they vanish. So the mass of these new particles, which you have 2 over 3 times n of, is just the confining scale, which is FA, which depends on phi. And go through a little bit of math. What you find is, I'm just going to call this 1 so I can get this. Lambda QCD is proportional to e to the some number 16 over 27 phi over f when n equals 8. Okay, so we know how the baryon mass depends on phi. We can figure out how the axion mass depends on phi. Find the minimum. So v prime equals 0 is derivative with respect to phi, lambda QCD to the 3 halves roughly. So, oh, I even have it here. The pion mass depends on the QCD scale times the quarks. So the axion mass depends on the QCD scales to the 3 halves, with quark masses being the other half, m quark to 1 half. This depends on phi, FA of phi plus times NA lambda QCD of phi and baryons. Okay, so we can just take a derivative. Derivatives of exponentials are easy. I chose this to be 1. This was determined entirely by beta functions. You can go through a little bit of math. You get 3 halves times this minus 1. You get 1 half. You just get 16 over 7 there. And what you find is, but you'll notice it's all multiplicative. So in other words, this is equal to some number times m axion, n axion, plus some number times m baryons, n baryons. And so this equals 0 is telling us the ratio of dark matter to baryons is equal to just some ratio here, which depends on beta functions. And it turns out for this particular choice, what you get is rho Axion over rho dark matter is 16 over 3, which turns out to be 5.333. I'm now going to write more decimal points than Josh did when he talked about this problem. Namely, the observed value is 5.36 plus or minus 0.05. So just a random amusing thing. Axions can very easily be dark matter. Notice I didn't have to say how is it produced or how are baryons produced, as long as they're both non-relativistic. This scalar will relax it to a number that happens to be within a percent level of the observed value. Now, you shouldn't believe either of these. You should ask what are the real error bars on both these measurements. This was one loop beta functions, etc. So it's probably closer to 10% error bars. The actual measurement assumes lambda CDM. There are 10% issues with lambda CDM right now. So either way, they quote percent level error bars. You should probably take it to more like 10%. And there's probably of order 10% things if being more careful. It's just amusing that you take Kim's original composite Axion model, supplement it by one coupling, and it just turns out to give this factor of 5. And I won't mention it since we're basically done. But this basically works exactly in the region that Ben said Axions are really annoying to do. Namely, this turns out to really work cosmology. I'm not for cosmology reasons. This works for roughly less than 10 to the 11 GeV. But yeah, okay.
Some idea why it happened, why we have, is it primary action or, but it's a lot of them in it for dark matter, right?
So here what you're doing is a scalar is just changing the mass of the baryons in Axion until the energy densities are equal. So you can start off with them being 10 orders of magnitude different, subject to rather stringent assumptions that we can quibble about later. It actually just will take those 10 orders of magnitude, change the Axion mass by 5 orders, change the baryon by 5 orders until they're a factor of 5 difference in energy densities.
So the line here, you just had a couple to the SU.
Yes.
Not QCD.
Yep. So all it does is change FA. Because FA is connected to QCD by the Axion in basically a rigid way, this also changes lambda QCD. Yeah.
But this thing could also couple with QCD.
Yeah, that's right. Well, there are other complaints probably that you would write down before then. Namely, I didn't write a vacuum potential for it, and this is no shift symmetry or anything protecting it. Yeah. Yes.
Yeah, I had a question related to the potential. If the baryons are thermalized, you should have some, like...
Great, so this is non-relativistic.
For a fixed number density.
Yeah, so this is also, more importantly, just the non-relativistic assumption. Yeah. And so as soon as it's non-relativistic, you also aren't really producing baryons out of the thermal bath due to Boltzmann suppression. Right. But if you try, this only happens after everything becomes non-relativistic. So the cosmology is a bit of a mess because you don't have much time between GeV scale and BBN. Yeah.
Yeah, maybe that's another. What temperature does this relaxation happen?
Whenever they're both non-relativistic, which depends on production mechanism and thermal history. So you might have produced the axions thermally, and then they're going to be very hot. You have to wait for them to cool down. There's basically no time. Okay. You can do it. Baryons, you have to work a little bit too. That being said, given that you might be changing the mass of the baryons by 5 orders of magnitude, if their mass was originally 10 to the 6 GeV, that's a little bit easier to make sure that they're non-relativistic. But yeah. All right, I think people are probably hungry, so let's go eat.